should only deal with things that seem to make some sense to us. And the potential energy, as near as I can tell, the main value of it was two. One is that most things that we actually deal with in our real life, we don't really deal with electric fields directly. As I mentioned to you, for example, if you buy a dry cell, a battery, it will say on it 9 volts. Now, volts are an energy. It's an energy difference, actually. And again, coming out of the wall of power is 120 volts. They don't tell you the field. They tell you the voltage. It's an energy difference. And the point is that you have an energy difference, and things tend to go from high energy to low. So you can deliver current. The voltage acts as kind of a pressure to move electric charge from one place to another. That's the easiest way to think of what voltage is. Now, I motivated that by giving you the example of if you throw something up in the air, it converts kinetic energy, a half mv squared, into some energy related to the height. Actually, it's related to the force that the field applies to this thing times the difference in height that the thing achieves. So it's stored somehow in the height or in the amount of motion that thing has. This is the force. This is a little bit tricky part of this definition. It's the force of the field on the object. So, but then the potential energy, or U, as we sometimes symbolize it, is given as the negative of this work. This quantity here is known as work. Again, not the usual street meaning of the word work, but it's a force acting through a distance. And in order to get the conservation of energy law to work, to look good, we have the change in the kinetic energy plus the change in this potential energy will be zero. That's the law of conservation of energy. Namely, if you lose kinetic energy, you gain potential energy. If you lose potential energy, you gain kinetic energy. And that's why we have to define this in this funny way. It's the negative of the work done by the field. Now, it just works out that way nicely, because then you can write a law like that. And if you do that, it makes some problems very much simpler. I wanted to do one problem to illustrate how you get the potential energy and how it might be useful. This problem will serve a couple of purposes. What I'm going to do is set up a problem like this. This is not in the notes or it's not in the book either, but I think it's an instructive problem for where we are. I'm going to set up our usual simple electrostatic situation, namely 2 flat plates on which we'll put charges. In other words, a surface charge of minus, say, here, and plus over here. The nice thing, as you've already seen how many times, is that the field inside is uniform, so it makes it for a simple problem. And we know that the electric field lines go from plus to minus inside this situation, inside this geometry. And it's pretty uniform. That's why we choose this. In fact, you have a problem, I've just worked with Monica on that, of an infinite sheet or thick plate of charge, and you found in your homework that if you had like a wall of charge, the electric field outside is nice and uniform. And that means that it was the same all up and down, and in fact, even out to infinity, in front and back, it was constant. Sort of, that's what we're dealing with here, because it's easy. Okay, now, let's see, how shall we do it? Let me say that I put a certain amount of charge on these plates. Let's make the area of the plate A. And I put a certain amount of charge, Q, on these plates. I put plus Q over here, and I put minus Q on here, total amount. So now we can define a surface charge density. Because these are areas, well, you know that these are conductors, by the way. Let these be conducting plates. So the charge will go, be able to move around. Now, if I put, like I charge this up, say with the Van de Graaff or some other means, the charge can move to where it wants to go. And if I put negative charge on this one, where they'll want to go, these charges will want to go to this face because it's closer to the pluses. Pluses will go to this face. So actually, if you look sideways, the pluses will all be here, and there'll be no charge, actually, on the back sides. Why should they go there if there's nice negative charge to attract them? In fact, that's how the thing will go. Okay, so all the charge we put on here will be appearing on this surface, whose area is A, so we can define the surface charge density as Q over A. So there's an example of a surface charge density. Okay. All right, now I want to find the potential difference. If I put this much charge, I know that there's a potential here, because suppose, for example, I'm a plus charge, for example. If I move toward here, I'm moving against the field. I'm sort of like pushing on a spring, and I get more and more, the field is, I'm fighting the field. So if the plus charge ends up here, he has a high potential to be pushed away and come down. So if I move a plus charge up here, he's increased his potential and his potential energy. Okay, so I want to calculate that in this case. And I want to use a number of our techniques that we've developed so far. So in order to get the change in potential energy, is the integral, or, yeah. Well, now I'm making the notation a little bit more complicated. It's the force of the field on the charge, and it's the force times the distance I travel, and it's a vector sum. This vector product, vectors. It's actually it's two vectors which, when multiplied together, in a scalar form. In other words, it's the component of the force along the distance. If I move this way, I don't really need any force to do that, because the force is pushing me down, right? So it actually is the force along the trajectory that I'm going. Now, that's called the potential energy. Now, as you recall, we defined the electric field as the force per unit charge. So we're going to define yet another thing, which is called the potential, which will be the change in energy, the total change in energy per unit charge. Because you see, the change, what we're trying to do is set up a kind of a field due to these plates. It's going to set up a field between them, independent of what you put there. But later on, if you put a charge in here, a Q, then you'll get both a force and an energy. But the potential, V, is the energy per unit charge. It's a way of talking about the source alone, right? This is the energy that the source is setting up, energy field that the source is setting up before you even put a charge in it. Such that when you do put a charge in, you will get a U if you multiply the V times the charge that you put in. So it's the same trick we used to go from force to field. Okay? Good. All right. So right now, in order to get, I want to get the field in here. Because that will be independent of what charges I put in. The field just depends on the charges that set up the field. Or the V is also due only to the charges that set up the field. So what is V? V is equal to, as I say, or actually it's a change, it's a difference between, it's the difference in energy between 2 points as I move between 2 points, pushed by that force, acted on by the force. So, since du is equal to minus the force, well, it's not a circle, it's just an integral. Why did I do that? It's just a path integral. It's not sorry, folks. It's not there's no surface involved here. It's just a single integral along a path. Sorry. It's just a force from times dx. Now, in the electrical case, this could be this could be gravity force or anything you want, conservative field, but in our case, the force is equal to the Q times the electric field times dx. So that's what we're talking about in electric case. So if you want to get the V, you have to divide this by the Q, that sort of a test charge, and they will go out. So that the equation I'm getting to is E dot dx. So in order to get the voltage difference, sort of this potential difference between 2 points, energy difference between 2 points as set up by this the charges, this delta V, between how much per charge the energy will change, I have to integrate the electric field between here and here. I have to get the electric field times the distance I move, and that will tell me the potential difference. So these are all definitions. I hope you've seen these in the book, or if you read it, it's there. Okay, so we have to, in order to get that, we have to know E. So here's where we're going to use some of our previous knowledge. Let me go back to here. Because again, we're looking to try to get the integral of the electric field times the path we go on from, say, A to B, and the negative of that will give us the change in our voltage. But so, as I say, first we need to know E. And I said we put on these on here Q over the area A, or sigma of electric charge density. And I make this minus for some reason, and that'll be plus, okay? Now, the question is, how can I find the electric field to do that little integral? Here's where it turns out, now, let me just recapitulate our story. In order to find an electric field, we have so far two means of doing it. We can either do it by Coulomb's law, because as you recall, the Coulomb law is that the electric field is given by a charge over R squared. And you have to add up all the charges. From all the charges, and you can get an electric field. Or we have Gauss's law, where if you have a piece of charge, if you make the surface integral of E times the area, it will tell you the charge inside. And by clever use of this, knowing the charge inside, in very symmetrical cases, you can find E. So those are our two ways of finding E. Now, in this case, it's pretty clear to find the E here, you don't want to use Coulomb's law, because that would involve finding every little piece of charge on this surface, adding up all its fields at a given place, summing them all up vectorially, and getting E. No, you don't want to do that. Unless you want to start young and want to end up old, you don't want to do that. So, but fortunately, in this case, we can use Gauss's law nicely. And I want to show you that because we haven't really done it quite yet in a nice way. But it's very similar to your homework problem. Now, the point is that this is a conductor. And we said that in a conductor, and that's the part we haven't done in class yet. How do you do Gauss's law with a conductor? That's nice. And the point is, inside a conductor, inside, E is equal to 0. And that's nice, because if you then have to do a Gauss thing inside a conductor, E is always 0, so that flux is going to be 0. That's a handy thing. If you go inside the metal, and you have to do E times area, E is 0, poof, the flux is 0. So how does that help you? Okay, let's go to this. And we say, all right, E is 0 here. Now, okay, the other interesting thing is, what does E look like? Another symmetry thing that we can do. If sort of symmetry. What is E at the surface of a conductor? What does it look like, roughly? Parallel, perpendicular, at an angle? What could it be? Interesting. Think a second. What? Perpendicular surface. Now, why? Well, also, let me make the stipulation that the charges are not moving. Everybody has settled down as to where they're going to go. Pardon? Say it again. Shortest distance is one way of looking at it. But look at this. Suppose it were that way. Then it would have a component along this direction. And if you have an E field, there's a force on the charge, so the charges would be moving. Contradicts the idea that they're still. So if the field is perpendicular, they can't get out. They can't move along the thing. So it is necessary in a static situation. This is a point I hadn't made before, but it's quite important. In the static situation, the electric field on a conductor is always perpendicular by the definition of static. Because if there were a component along the line and the charges are able to move, they'll move. Now, this doesn't hold for an insulator. An insulator, the field could be at an angle because the charges can't move. So they could be stuck, and even if you put a field there, they're still stuck because of the insulator. But in a metal, no, you can't have a sideways component. It must be perpendicular. So that's a good point, and something that comes in handy when you do problems. So we know that it looks like that, and that helps, because when we apply Gauss's law, we always want to put our surfaces, when we create a Gaussian surface, we always want to make our surfaces either sort of parallel to the lines of force or perpendicular, right? Now that we found out what direction this is, we can choose our Gaussian surface in a smart way, right? Now, what would be a smart way to pick a surface that is parallel or perpendicular to that line? What kind of a surface would you put there? Any ideas? How about, well, you want to have some of the lines parallel, and you want to have some of the lines perpendicular. That's good, because, again, you know why? Because when they're parallel, no flux goes through that surface, and when it's perpendicular, it just goes through. So let's pick that. What did you say? Cylinder? Yeah, cylinder is good. Yeah, cylinder. Pillbox. In fact, it won't really matter much what shape it is at all. All it has to be is parallel or perpendicular. I can make it wiggly. But as long as I make it perpendicular, and I want to go inside too. gig, like that. Okay, it doesn't matter really. As long as they're the same. See, this is an area and that's an area. Doesn't matter, because it's going to cancel out. But I've made the situation where the lines are parallel to the field or perpendicular. That's all I really need. And you'll see that the area, giggy area or cylindrical area, it won't matter. Okay, so we're going to find by Gauss's law what the electric field is outside the metal. Now, inside the metal, we know it's zero. That's nice. So let's write down Gauss's law, which is to say electric field times the area is equal to the total charge inside over this constant. Okay, now we do our trick. We just find all the different surfaces. Let me do the giggy one here, this one here. I have the sides, and I have the end. Let me call that end. Again, I keep calling it A and B. Well, that's poor notation. End outside the metal, and I have an area A inside the metal. Okay, so let me just add up all the E's and the areas over this surface. Let me start at this one. Well, it's E times this giggy area, okay. But E is zero, so that's zero. Nice. Now I look at the sides. They are parallel to the normal on that is chosen to be perpendicular to the lines. So over the sides times the area of the sides, but the E and N are perpendicular, so that vector product is zero again. So there's no flux through the sides because the lines just shoot by. So all you're left with is the top part. Whatever that field is times the giggy area, whatever it is equal to, that's the total flux. So right? We clear? Good. Okay, now we have to find out what's the charge inside that we've captured by putting this surface over the charge. What's the charge that we've captured? Also, I passed through the surface. You see, I actually passed through the surface, but fortunately the field is zero over here. So I don't have to worry about that. I don't worry about those because the lines are parallel. I just worry about this, and I have a certain area here. But I also, this is the area I've captured as far as the surface is concerned, right? The same area. So I get the Q now by the Q is now the surface charge density times the giggy area, whatever it is. And so I take, this is my net flux, and I put it into my captured charge, sigma A giggy over epsilon naught. And the areas, as promised, cancel out, and I get that the electric field in that at that place here, I come to here, the electric field in that space is equal to sigma over epsilon naught. That's the field inside these two plates. And it does not depend on the distance, which is like the problem you did with the wall of charge, where it didn't matter, the field didn't matter as you went out and out. In any case, the field here on this surface is sigma over epsilon naught, and it's sigma over epsilon naught here, and it's sigma over epsilon naught here. inside the area. It's a uniform field, constant through here. Now, near the edges, things get different. I mean, the field will buzz, but let's just concentrate on a very big area, and we'll concentrate the field in the middle. So here is how we've used our Gauss's law with conductors to find the field inside this geometry, inside this. All right. Now we go back to here, and knowing that field, we can now calculate the potential difference as you move along. So our delta V is equal to minus the integral of E times dx. And I just calculated E over here, so it's minus the integral of my sigma over epsilon naught dx. So we can take our x from, say, make x in that direction. We can call that 0. Again, well, there's another point, but and let's say the separation of these plates is our distance d. We could stop anywhere, actually. Well, let's say to some place in the middle. We'll call arbitrarily to some value x. And the plates are separated. So the voltage difference between 0 and the point x is equal to this. And that's very nice because sigma is a constant, epsilon is a constant. We take them out of the integral. And you just integrate dx from 0 to x. Even I can do that. Is just x. So with a minus sign. That's your delta V. And our delta U is minus. Well, okay. That's it. That's what I wanted. I got to be a little careful here. Now, in this case, I chose sigma to be negative. So if sigma is negative, delta V is actually going to be increasing positive. Now, if I move up an x, and that's correct. See, remember I said if you move a positive charge in this setup, if you move a positive charge upward, I'm adding potential to it, and so that really comes out here because my delta V is minus sigma over epsilon x. As I move increasing x, if sigma is negative, then delta V is going to become more positive, and that's a good check. Do we get that? So this teaches us a lot actually about. First of all, how to calculate E in a special case, something about the electric field at a surface of a conductor, that it's perpendicular. We use Gauss's law cleverly by choosing the right surface and knowing the direction of the field. We could get the electric field in that relatively complicated situation. So that's delta V. Now, I think that's a relatively simple situation. And you see, this is actually rather similar to that of a mass in a gravity field. Again, the gravity field is pulling down. If I increase x of this chalk, I am increasing the potential energy or the potential as in proportion to the height. That's what we showed the other day. It's mgh, remember, for gravity. So instead of mgh, we have basically x is like our h, and this is sort of like the attraction g force. It's representing the sigma is representing the attraction of the Earth, or the attraction of the charge in this case. So it's very similar. That is that in a uniform field like this, the potential energy increases as the height that you move against the field. So it's very similar to that case of the gravity potential. So you can look at the book or my notes here to get a little more feeling for the subject. And the V, okay, we went through all of this. Now, an important case that you have to know, in addition to this two parallel plates, the other popular case is the point charge, the potential of a point charge. And we do the same thing here. If you have just, say, we think of the potential of a positive charge, and we know the electric field at any point out here is going to be given by Q of this charge, K, or 1 over 4 pi epsilon naught, over R squared. Now, to get the change in potential, if you want to know the potential at that point, as compared to the potential at infinity. See, the potential, you always take a potential difference. And if we take the potential at infinity, 0, we can get the change in potential in going from here to infinity. In other words, V of infinity minus V at R is equal to, our law is, take the electric field and you times the distance through which it acts from R to infinity. In other words, I'm going to start here at R, and I'm going to move a charge, a positive charge, out to infinity. I'll end up at V at infinity, but I started with V at R. So this is the integral from R to infinity of this. And you just, that's what I'm going to do on that slide. So E, we plug in as KQ over R squared, dr, and the field, in this case, of a positive charge is in the same sense as the radial vector, n of dr. They are parallel, so that vector, you remember we had a unit vector attached to the field. Those are parallel, so there's no cosine problems. And you just integrate that. The integral of r to the minus 2, kq, r to the minus 2, is r to the minus 1 with a minus sign. So you just get your minus 1 over r with these q from little r to infinity. And so you get your plus kq. Now at infinity, this is 0, and this is at minus r, so you get a minus sign coming out here over r. This is just math now. This is a little harder than what I did before with the uniform thing. Sorry about that. But it shows you that even if the field is not uniform, see, this was the easy case because the field was uniform, and this integral, as I said, even I could do, just dx. This is a little harder. This is 1 over r squared dr. But it's also something you learn in Calculus 1. So what you end up with at v of infinity is 0. You get a minus v of r is equal to minus k q over r. And so we can change the signs of these. And this is the thing you really have to know. This is the potential of a point charge, and the reference 0 is at infinity. So that you have to know. It's an important result. So what it means is that the energy at a certain distance r from a point charge just depends on r. Right? So if you have a point charge, the energy at any distance r is the same all along this because it just depends on r. And as you go out, it gets less. Your potential gets less. So the potential has the shape shown in my slides. Let me better show it on the slides. It'd be better than my messy diagram. You see, what we've done is we had a charge. We've moved the charge from r to infinity, and we've calculated what is the integral of that field. So the lines of field look like this, but the lines of constant potential are circles, and they get closer together. In other words, the potential gets higher because it's going upward as you get closer as 1 over r. So if you go half as close, you double the potential. Here's another view. Oh, I overshot. How the potential increases as you get closer. And if you put a positive charge there, it's going to slide down the potential curve, which says that the field is pushing you away down the potential curve. Now, the usefulness of it is the fact that this potential energy plus the kinetic energy is constant, and the change in one is the negative of the change in the other. And I did set a problem. Why don't you try to do this yourselves, where I set up the problem, which could be quite hard if you do it with forces and Coulomb, but turns out it's easy to do with potential energies, or potential energies, in fact. That is, of two electrons, say, having negative charge, and I go to infinity, be right back, and I put another electric charge back here, electron, and I shoot it at these things here along the axis, and then, but I want the conditions such that since it's being repelled, that charge as it approaches being repelled by these people, pick the velocity there so that it just stops here. Now that would be a very hard problem, as I said, to do with Coulomb, with forces, because as you're moving in, your force is changing in magnitude. You get closer, it gets bigger, and in fact, and then it turns around and gets smaller, and the angle is changing and all that. Very hard to do. But with energy, it's not hard at all, because what you do is you say, I start out with a certain kinetic energy and a certain potential energy initially, and I end up with kinetic energy plus potential energy at the end, or I could say delta KE plus delta PE is 0. Those are the same thing. So what's happening here is, my question is, if I start out with a certain speed, which I don't know, V I don't know, that's the question. How much V will I use up? I have to go down to V equals 0 here, but I started at infinity. So my potential energy here is 0 by definition. See, I'm dealing with point charges. So I've assumed that the potential energy is 0 at infinity. When I arrive here, it stops, so the V is 0, but then I have some potential energy, which I can calculate because this is a charge, E, and I know a distance, and so I can find the potential at, let's say this distance separation is D. The potential of this charge, V, at this point is equal, I just calculated, to K, Q, in this case it'll be E, over D over 2. In other words, this charge here, let me call this guy number 1 and number 2. The potential due to number 2, say, is kq d over 2, right? Do we understand that? Now, okay, the q will be minus in this case, so it'll be a negative potential, but that doesn't matter too much. And then the potential due to charge number 1 is likewise given by the formula for point charges over d over 2. Now, the thing that's beautiful about potentials is that they add, so that the total V at that point there, at 0, is the sum of these two potentials, V of 1 plus V of 2, algebraically. So I just add those two together, and I get KQ over D over 2 times 2. Because the two add up. And that's okay. So that is the potential. That's the potential. If I multiply that by E of this incoming charge, it'll tell me that the potential energy that this charge has accumulated. In fact, you see, it's working against the field. The field is pushing it away. Its potential built up. And so that will give me that the E of that charge times the V that I just calculated here at 0 has to be equal to the initial speed that I put in. And if you just solve for V squared, you will, and you see, you put in your E's and so on. You will get the thing. So, what time is it? I have 5 minutes. I've got to show you a couple of cute things, though. Let me leave that. The answer is actually given in the notes. And also I have various analogies to what potential is. Potential is sort of like pressure. And you can think of air pressure. Have you seen maps of barometric pressure and the winds blow across the lines? Same kind of thing. The potential is like barometric pressure, and the field lines are blown away down the potential. Now, I have to go over to a different PowerPoint. I want you to start reading about currents and voltages. So let me put this guy away. And I hope I have it here. Yeah. Let me begin with this. I wanted to show you this little setup. I think you'll like this, because I do. Let me skip ahead. I'm now going to start to talk about electric circuits, but the first thing you have to know is that we're switching to a situation where the charges and the voltages, the charges are moving. Up till now we said the charges are stationary and so on, with statics. Now we are going to worry about charges that move. And you have to push the charges to make them move. So you have to have some kind of what we call electromotive force, which, well, one way of doing it is you can have, like your Van de Graaff generator, you can, by friction, build up charge, and those charges push other charges. For example, we got a lightning sparks from one ball to another, because the charge is built up, and it builds up this voltage, and it breaks the air down. That's a painful way of getting electricity. The great discovery was in 1780, that's what I thought the golden age of electricity, really, when Galvani, you know this story? Galvani? He was a doctor, and he was an anatomy professor, and he was dissecting frogs. And he probably had a scalpel in one hand and maybe a clamp or something in the other, and he took this freshly dissected frog's leg and started cutting, and he saw the frog leg jump. That would have scared the hell out of me, and he did it again. He said, "What's going on here?" That's a great question. What's going on here? So that's what you want to ask. And he didn't just forget it. But what he thought that what's happening is that, people do move. So they thought there's a sort of a life energy. And he thought by sticking these two things in, he was releasing the life energy and made the thing move. That was his thought. And he published this thing that there's this life force, and he released it by cutting into it two things. Well, it turns out, so that was his experiment, Galvani. But then along came a man named Volta, another Italian. That's why I played Vivaldi's music too, because it's Italian day. Volta heard about this experiment and said, "Wait, that doesn't sound right to me," because he started playing with it, and he found out that different metals cause different effects, and he didn't like that approach. So let's see here. Oh. You can't, well, maybe I can erase quickly. I hope you guys can stay. I'll keep you out of the rain a few minutes. This is a meter. Let's see if I can make it a little darker. A little better, maybe. So, let me just show you what this meter does. This is a meter, you'll be using something like this. It's a voltmeter. It measures sort of, voltage is sort of like a height difference. So you have to be across something and measure its energy difference. And to show you what it does, I have here just an ordinary 9-volt battery. And these are the connections to the battery. So if I touch one, see if I get it right. Oh, I went the wrong way. Okay, let's. It has a sense to it. Up, there's plus or minus. Okay. Okay, that's a 9-volt battery. Right. So that's what we're accustomed to. Now this is more or less what Volta did. Now this is my frog leg. Well, anyhow, it's a juicy living. It's a juice. Basically, all you need is juice, or acid, or salty water. But so this is more like what Volta did, or Galvani rather. So he was scalpeling this thing, and let me try to find see. See, you get a voltage difference. This is actually like a battery. Why? Well, Volta finally figured out that what it was is the fact that he was using two different metals. See, this is copper, and this is iron. He probably had a steel scalpel or an iron scalpel and maybe a brass tweezer or something. So he was going between brass and iron, and there's a different affinity of charges to one to the other. And if they can get through the juice, they will. And in a frog, if you start sending electricity through a frog's leg, he will jump. So that's what Volta does. So this is the frog's leg. It jumps when the juice flows, the electricity flows. And that's why my father and mother called it juice. Maybe they knew about Volta. I'm surprised. But the cute thing is that when I heard about, now if you look in the book, there is this experiment with a lemon. Now I have a lime because they happen to be on sale. And but it works for everything. I mean, I tried apples. Okay. Wow, look at the apples are good. That's 0.6 volts. That's not as much as a regular battery, but that's damn good. And I even tried banana. I should have tried this before. And you would think banana doesn't have much acid in it, but that's good. Bananas are terrific. Look at that. That's even more. So it's a battery. And that's your electromotive force. It's between two dissimilar things. And batteries have like a carbon rod. So sometimes you hear about lithium-ion batteries and this and that. It's a big science. If you can make a better battery, you will become rich because, for cars and your computers might last longer. So that is really important. And all it is you have two dissimilar things, and you allow the current the charges that want to go from one to the other because they have a greater affinity, you allow them to go through. In fact, this is a pretty poor conductor. I don't know if it, see, I really wonder why it doesn't, no, it doesn't work. Where to go? Oh, yeah. I don't know why it doesn't work through insulators. I mean, because these things should, no, that doesn't really, yeah. Well, apparently it has to have some little bit of a conducting path. And these electrolytic solutions, even a banana, seems to work very well. So Volta explained it in those terms, namely two dissimilar things. He would have it like metal, zinc, and copper, and if you put them in a row, you build up the voltage. Like, I got only half a volt. If I put three of them, I get a volt and a half. And that's what you do with your batteries, too. You know, you put them in a series if you want. And that's the giant, that is the breakthrough, because that makes electricity conveniently available in reproducible amounts. It isn't just rubbing and hoping. You just put your zinc in your copper and your zinc in your copper, you get it every time. That changed the whole world. That's the breakthrough.